Hello everyone, I'm Chu Han Wang from Tsinghua University. Today I will talk about our research on an email authentication protocol, DKIM. The title is a large-scale and longitudinal measurement study of DKIM deployment. Email service is one of the popular services in the internet world, and it is because of its important position that email service has also become an important target for attackers. To defend against email spoofing attacks, various email authentication protocols have been proposed and standardized in this year. At present, DKIM is one of the most widely used email authentication protocols. DKIM has been proposed and standardized since 2008 and is now adopted by Yahoo, Google, and other leading email service providers. DKIM signature is generated based on hash algorithm and asymmetric encryption algorithm, just like RSA. DKIM's public key is deployed on a domain name in the following format, just like that. The selector here is a random string specified by the domain owner, and example.com represents a real domain name. The image here is an example of a real DKIM signature. Next, let's take a look at the workflow of DKIM. First, the sender deploys the DKIM protocol. They need to generate a key pair by asymmetric encryption algorithm and then deploy the DKIM records, meaning the DKIM public key, on a DNS server of a specified domain. Second, when the sender's MTA sends an email, a DKIM signature is calculated for the outgoing email, which includes the email headers, the email body, and the DKIM signature itself. Last, when receiver's MTA receives an email with a DKIM signature, it also first accesses the DKIM records for the sender's domain to validate the DKIM signature. Although DKIM is an important email security protocol and it has been proposed for more than 10 years, little has been done to understand the adoption rate and the potential security issues of DKIM. In the previous works, they conduct the large-scale measurement of the other two protocols, SPF and DMARC, but DKIM was absent. This is because the feature of DKIM make it difficult to be measured at scale. From the previous description, we are able to know that there are two main ways to obtain DKIM information. One is from DKIM records, and the other is from DKIM signatures. DKIM records is deployed in this specified domain. Because the selector is randomly specified, it's difficult to measure at scale directly. Besides, DKIM signatures are also difficult to collect by researchers. DKIM signatures are embedded in the email header and would not be publicly released. It's difficult for researchers to obtain large amounts of DKIM signatures data for further security analysis. However, we find two ways to get DKIM information. First, we can pass DKIM records from passive DNS datasets. And the second, we can extract DKIM signatures from email headers. Therefore, we collaborate with our industrial partners and get the datasets. In total, our data covers 5 million distinct domains and 2 million distinct selectors. Our data collection and analysis process is shown in the figure below, which is mainly divided into 3 parts, including data collection, data processing, and data analysis. The data collection stage has been basically talked earlier, mainly through cooperation with industrial partners to obtain the corresponding DKIM records and the DKIM signatures. After data collection, we will perform a series of operations such as data cleaning, data aggregation, and deduplication on the raw data. Through the above passive collection stage, we found that there are many commonly used selectors such as mail, default, DKIM, which will be used by many domains. Therefore, we conduct a large-scale measurement of Alex top 1 million domains, use the top 40 selectors obtained from the passive collection. And finally, we can use the results of the measurement to analyze DKIM adoption rate, the grammatical problems of DKIM records, DKIM key management issues, and DKIM signature issues. In this paper, we perform a large-scale and longitudinal measurement study on the current state of DKIM. The results shows that 28% of Alex top 1 million domains have enabled DKIM, of which 3% are misconfigured. Besides, we also measure the adoption rate of SPF and DMARC by active scanning, and the results can reflect the current status of DKIM deployment from the side. The image here shows the change in deployment rates of SPF, DKIM, and DMARC over the past few years. Part of the data comes from the two papers listed below. To know more about DKIM deployment, we also analyze DKIM adoption of the domains under different country code top-level domains and genetical top-level domains. Next, let's talk about DKIM key management issues. RFC recommends that DKIM keys should be rotated on a routine basis. However, we found using long lifetime keys is common even for most high-profile domains. The below figure shows the number of long lifetime keys of Alex top 100 domains covered by our dataset. The orange part represents the numbers of keys that have not been rotated in the last 5 years. Finally, we found 10 out of Alex top 20 domains have not rotated their keys in the past 5 years. We also analyzed the DKIM key lines in passive DNS dataset. RFC has pointed out the short RSA keys more easily succumb to offline attacks, and signers should use RSA keys of at least 2048 bits. NIST has also recommended that. However, our research shows 84% of more than 3 million domains still use DKIM keys that are less or equal to 1024 bits, while more than 5,000 domains still use DKIM keys that are even less than 512 bits. We also analyze issues of DKIM signatures in practice based on 400 million real DKIM signatures from Comail. We find most domains have DKIM signature issues. For example, weak DKIM signatures are common. What is weak DKIM signature? DKIM signatures should sign important email headers to protect the content integrity of email and avoid being abused for replay attacks. However, RFC only specifies the from field to be must signed, although it also recommends the other 20 headers should be signed in the DKIM signatures. We find no domain in our dataset signing all of the 20 headers. RFC only provides a basic guideline that DKIM signatures need to protect the core content of the email message. Actually, we found that the header fields signing in the DKIM signatures vary among different email services. There is not a consensus in the actual implementation. Almost all of the domain have signed from and subject fields. However, only 11% of domains have signed reply to fields. To prevent adding duplicate header fields, DKIM designers proposed a method of oversigning, which means a header name should appear in each text once more than the actual numbers of that header in an email. There is an example of oversigning mechanism. The oversigning mechanism is helpful to protect the users from the email spoofing attacks. However, we measured how many domains use our signing to protect themselves against multiple headers attack. We found only 2.2% of domains in our DKIM signatures dataset used our signing mechanism. The last part is about mitigation and recommendation. First, we have tried our best to report all vulnerabilities we found into the relevant email administrators. 4 email vendors and 24 relevant email administrators have acknowledged our report. And second, we have developed an online tool for DKIM development based on our measurement and analysis scripts. This tool can help email administrators check and deploy their DKIM records and further improve the status of DKIM deployment. Now this tool can be accessed at nosebroofing.cn. At last, we proposed 2 improvements which may help to improve the protective effect of DKIM signatures and prevent DKIM signatures from being used for replay attacks. If you are interested in our work, please read our paper for details. I'm sorry that I can't attend the meeting in person because of the COVID-19. Please feel free to ask any question on the Slack and I will respond in time. That's all. Thank you.